Welcome back to part 2 of the lesson on exponential functions with base e. For a quick review, an exponential function with base e is in the form f of x equals a times e raised to the power of kx, where a is the initial value or starting amount. If k is positive or greater than 0, then the function represents exponential growth with a continuous growth rate of k, and if k is negative or less than 0, the function represents exponential decay with a continuous decay rate of the absolute value of k. Let's go and take a look at our second example. We're told carbon-14 has a continuous decay rate of 0.012097% per year. Suppose 15 grams of carbon-14 is present. Write the exponential function to model n of t, the amount of carbon-14 present after t years, how much carbon-14 will remain after 120 years, and finally, if 20 grams of carbon-14 remain, how old is the artifact? So because we know we have a continuous decay rate here, we can model the amount of carbon using an exponential function with base e. So for part A, we'll have an exponential function in the form n of t equals a times e raised to the power of kt. Remember, a is the initial or starting amount, so in this case, because we're beginning with 50 grams of carbon-14, a is equal to 50. And now for k, because we have a continuous decay rate of 0.012097%, k is going to be negative 0.012097%, but k must be expressed as a decimal, so as a decimal we would have negative 0.00012097. To convert a percent to a decimal, remember, we drop the percent sign and move the decimal point to the left 2 places, or divide by 100. Which means the exponential function to model the amount of carbon-14 present after t years is going to be n of t equals 50 times e raised to the power of negative 0.00012097 times t. And now we'll be using this exponential function, or exponential decay function, to answer parts B and C. Part B asks how much carbon-14 will remain after 120 years, and since t is equal to the number of years, we know that t equals 120, so to determine the amount of carbon present after 120 years, we need to find the function value n of 120, which would be 50 times e raised to the power of negative 0.00012097 times 120. So now we'll go to the calculator and approximate this function value. So we have 50, and then for e we can press second natural log, which brings up e raised to the power of. Let's go ahead and put this exponent in parentheses. So open parenthesis, negative 0.00012097 times 120. Now in the newer version of the 84 like I have here, the parentheses around the exponent is not required, but it is always nice to clarify that product is the exponent. So if we press enter, if we round to 3 decimal places, we'd have approximately 49.279 grams of carbon-14 present after 120 years. Let's go and write this as a sentence. After 120 years, 49.279 grams of carbon-14 will remain. Now for part C, we're asked if 14 grams of carbon-14 remain, how old is the artifact? So now we're given n of t when we determine the value of t. Here we're given n of t equals 20 grams. So we want to solve the equation 20 equals 50 times e raised to the power of negative 0.000120097 times t. And we'll actually solve this two ways. Just in case you don't know about logarithms yet, we'll solve this graphically, and then we'll come back and solve this using logarithms. So to solve this graphically, we would enter the right side in the graphing calculator in y1, and we enter the left side in y2, then we'd graph the two functions and determine the point of intersection, which will give us the value of t that satisfies this equation. So going back to the calculator, we'll press y equals. We'll clear out any old functions here. And in y1, we'll enter the right side of 50, second natural log for e, raised to the power of negative 0.000120097, and then times t, which we'll use x instead. So here's the x key, enter. And then in y2, we enter 20, enter. And before we graph, we do want to adjust the window. So let's press the window key. Now for the x values, let's go from negative 500 to, let's say, 10,000. And we'll scale it by 500ths. Now for the y-axis, we know the maximum function value would be 50 when t equals 0. So let's scale the y-axis from, let's say, negative 10 to 60. Let's scale this by tens. Now let's press graph. If this doesn't look good, we can always come back and change the scaling on the axes. So we'll press graph. So there's the exponential decay function, and there's y equals 20. And notice how we do have the point of intersection on the screen, so our window is fine. So we'll press second trace for the calculation menu, option 5 for intersection. Now we'll press enter 3 times. Enter, enter, enter. Running to two decimal places, x is approximately 7,574.53, or in this case, t. So graphically, we now know that t is going to be approximately 7,574.53, and this would be years. Again, let's also solve this algebraically using logarithms. So to solve this algebraically, the first step would be to isolate the exponential part, which means we would divide both sides by 50. And simplifying, 20 divided by 50 is equal to 0.4. We have 0.4 equals e raised to the power of negative 0.000120097t. Now here's where we're going to use logarithms, and because we have base e here, it'll be more convenient to use natural log. So we'll take natural log of both sides of the equation, and now on the right side we're going to apply the power property of logarithms, which allows us to take this exponent here and write this as a product where we have the exponent times the natural log. So we have natural log 0.4 equals, here would have negative 0.000120097t times natural log e. But because e to the 1 equals e, natural log e is equal to 1. Therefore, in order to solve for t, we just need to divide both sides by this coefficient. So simplifying on the right, we just have t, and now we'll approximate this quotient on the graphing calculator. So back to the home screen, and we'll press natural log 0.4 divided by negative 0.000120097, enter, and of course we get the same answer that we did graphically, approximately 7,574.53. Again, this would be years. So let's answer the question as a complete sentence. If 20 grams of carbon remain, or carbon-14 remain, the artifact is approximately 7,574.53 years old. Okay, I hope you found this helpful.